So the screen is visible. So today we are going to start with this topic, essentially in some way continue from what we were doing yesterday in terms of doing a complexity analysis of these CNNs. Now, I mean, all of you or most of you in general have done something on complexity analysis in programming and data structures or some other advanced courses as well. Okay, so now how many types of complexity are you aware of?
Like time complexity, space complexity.
Okay. So one is space complexity. Another is time complexity. Okay. Now we'll start with each of them. What will space complexity define? So space complexity will tell me how much of memory is needed in order to run this code. And time complexity will give me how fast can it be executed. So now, and then these are again two different aspects over here. Okay. So now, in order to analyze space complexity, what do we need to understand? So in a CNN, so say that I have a input X, it goes into a conf layer and out produces another tensor Y. So in order to do space complexity analysis, we'll have to find out space needed by X. We'll have to find out space needed by Y, and definitely space needed by all of these bits P's. Okay, so let us go ahead. Now look over here. So say I have a convolution operation over here, which is defined as, so I take down conf 2D, and then there is some width W, height H, stride and this is what I know about this conf 2D operation over here. Now input comes a tensor X, which has what? It has C number of channels, has M number of rows and N number of columns. and this goes into this, and out comes another tensor y, and okay, so if number of convolutions is equal to k, then this one is k, this is OW, and this is OH. So now, what is the total space required to store this X? So this is CMN. Okay. What is the space required to store Y? It is KOWOH. Now, if I put down my OWOH, then what should it look like? So this will, OW is going to be N minus W plus 2PW by SW plus 1 into M minus H plus 2pH divided by SH plus 1. Okay. Now, next question is, what is the space required by P? So there are k number of convolution kernels, each with a size of C cross W cross H, and the space required for the bias, which is, so since there are k number of convolution kernels, so there are k biases which get stored over here. So am I correct with this? Do you agree with me? And to make things simple, let me write down that X belongs to R power of C cross M cross N. Here P belongs to R power of K cross C cross W cross H, and bias belongs to R power of K cross 1, and Y belongs to R power of K cross OW cross K cross OH cross OW, and this will be H cross W. Okay, so if this is the condition, then this is what I require. Now, in general, you have understood how much of space will be required over here. So now let us solve this one for a practical network. So let us look into Lec9 5. Okay. So your input X belongs to R power of 1 cross 32 cross 32. And how is this Lec9 5 defined as? So I have my input which goes to 6 convolution channels, each of width 5 cross 5 with 0 padding and stride of 1. This goes to max pool 2W 2S. This goes to 16C 5W 0S 0P 1S 0P 1S, and that again goes to max pool of 2W 2S. This whole thing again goes to fully connected. Just a minute. Now over here, after that max pooling, what do you connect? You have 400 neurons. So 400 neurons are fully connected to 120 neurons. Then you have 120 neurons which are fully connected to 84 neurons. And then 84 neurons are fully connected to 10 neurons. And that comes your output over here. Now, if this is how the whole operation is being defined, now on top of it, you had found out what is the total number of parameters, and that is going to give you what is the amount of space which is going to be required to store only these learnable models. But here, I will also be needing to store each of these outputs over here from each stage. So now let's look into what will be the size of input. So my size of X, which is my input. So this is what I have as 1 into 32 into 32. So what is 32 into 32?
1024.
1024. And these are elements. I'm not yet considering them to be bytes or anything. It depends on what is my precision of the number system, based on which this can be defined. Okay. Next is, so I will need something to store this first convolution layer. So let me write. So this input, this is what I call as X. This first convolution layer is what I called as P1 and B1. So size of P1, B1. So what is the size of P1, B1 going to be?
156.
156. Okay, good. Now from here I get an output which I call as Z1. So what is that size of Z1 going to be? So now,
4704.
so what first is we need to find out what is this Z1. Okay. So Z1 is of the size of what? So you will have 6 channels into this was what 28 cross 28. This is what it was. So that is going to be 6 into 28 into 28. So what is the size? Can you please tell me once again?
4704.
4704. Okay, good. So now here onwards, look over here. This operator over here, this max pool, that does not actually store anything. Okay, so if this is not going to, so there are two instances in which it can either store or it may not store. So if I want to preserve the indices, then it might store something. If I don't want to preserve the indices, then it might not store. Nonetheless, it produces an output over here, which we call as Z2. Okay. Now, what will be the size of Z2? So what is Z2 going to be?
Sir,
6
cross
cross 14 cross 14.
1176
1176.
76.
Okay. Now, there is a condition in which what you do is you also store the location from where this maximum value has come down. In that case, this will just be double of that because you will also have locations. But in general, you again need to consider about the pointers. So we will get into that a bit later on. Now, the next point is this whole thing, if I call this as P2, comma B2, then what is my size of P2, B2?
2416.
2416. Okay. Now the output of that is going to be called as Z3. Now what is my size of Z3?
1600.
1600.
Now from there I will get down Z4. Now then I need to find out size of Z4. So what is that going to be?
16 cross 5 cross 5.
Sir,
It
400.
is 400.
This will be 400. Okay.
Yes, sir.
Now from there, this will be, if I call that as W1B, or for convenience, let's call this as W3B3. So I have my size of W3B3.
Sir, we should
Yeah.
also include the size of that flattened layer 400 cross 1. That one.
No, what is
After
flattening?
Z.
No. You need to understand. So what is flattening doing over there? Flattening is not retaining anything. It just did a sort of a reordering in how you are storing the number system. So when you have a 2D matrix, what do you have? You essentially have a row major or a column major. You have a header over there which says that what is your row size and column size. That is how you are able to reconstruct a 2D thing. But for storage purposes, for storage purposes, it is not essentially showing you anything in different ways. So there is nothing called as a two-dimensional memory orientation. And it does not even copy one thing from one place to another place.
Okay.
That
So
is
after the flattening happens, Z4 isn't there anywhere. Means this 16 cross 5 cross 5 won't be there after flattening.
yes.
Okay.
So, um, hello,
Tell
sir.
me. Yes.
Can you explain that max pooling layer why it is not preserving the space?
Max pooling layer. Why? What will it not preserve?
The means why we don't calculate the space and like that.
So is there any learnable parameter in the max pooling?
No, sir.
Okay. If there is no learnable parameter in the max pooling, then will it take any space?
Okay, sir.
Okay. So now I look into W3B3. So what is my size of W3B3?
Four eight one two
48120.
Once again, please.
48120.
48120. Okay. Now the output of that goes into Z5. So size of Z5. What will this be?
120.
120. Good. Now this one is W4B4. So what is this going to be?
10164.
From here I have Z6 and this one is W5B5 and from here I have Y. So now let's do it. Size of Z6 is 84. Size of W5B5 is equal to 840 plus 10 850 and size of Y Size of y is 10. Okay. So now just sum total. So what is the size of this network?
Sir, 70,824 is the total parameter number.
Yeah, can you tell me once again, please?
Seven zero eight two four.
Okay. So now say that my precision.
Sir, I had a doubt.
Yeah, tell me.
Sir, output of the after flattening does not require any additional space, but output of max pooling does require space. Why is that, sir?
What is max pooling going to do? So max pooling takes in a particular size tensor and changes it to and on the output you get a different size tensor over there. Okay. And what does flattening do? Does flattening change the nature of a tensor? Does it operate anything over there?
No,
Wait.
it
Let me write and explain. So max pooling, what is it doing? So say I have 2 by 2 max pooling over there. I will get a single sized element over there. So essentially there is an operation which is of a fixed type without any learnable parameter. So this is the same thing even for your linearize or flatten operation itself. Okay. But here, if this is my input and this is my white output, then I have two different set of input and output. There is some operation which is happening over there. In case of flattening, what do I have? I have this X. I just write it in this form in terms of X dashed. Now there is no parameters.
and this to this is just a column measure representation. So do I need a separate space to store? Because in my RAM, anyways, both of them are just stored in memory. So this is my address, this is my val, and my RAM is a linear RAM. I don't have a two-way addressable RAM. I just have a one-way addressable RAM over there. So because I just have a one-way addressable RAM, so I don't have any change as such which is happening. Is that clear, or you're still in doubt?
So, the thing I was thinking about, sir, both of them are sort of similar operations only, meaning that they don't have any parameters. So still I'm a bit unsure why max pooling does require much space. New
No,
space.
max pooling does not require space to see. It does not require space to store any of its operands inside. It
Yes, sir.
requires a
But
space to store the output.
yes, sir. Why is
There
it
is
requiring
any
this? Why is
because
it
your
requiring this
output
space?
is your output is, so say in my input I have 4 elements. In my output I just have one element.
Okay.
Do I have all
Okay.
the 4 elements which are over there?
Okay, sir. Yes,
But in
sir.
case
Now
of
I understood.
Lightning, there is a one-on-one relationship. Every single element on the input is mapped to another element in the output. And that mapping is also unique. That is repeatable and well defined. In case of max pooling, it is not well defined because it depends on what value you got in your operating space, that value will be put down over there. If it was the same value which was, so say there was a, instead of a max pooling, there was a subsampling, which is I will pick 1/4 of the values, but I will pick it deterministically. So in that case, I would have said that you don't need additional memory.
Okay, sir. Now I understood.
Okay, good. So now if I have a certain precision, say if my precision of number system is equal to B. So if I'm operating in double precision floating point system, then that is FP64. So there are 8 bytes, or say single precision floating point, then it's FP32, which is 4 bytes. If I'm doing in half precision floating point, then it is FP16, which is 2 bytes. Then I can have it in integer. So integer can be int 16, then also it will be 2 bytes, or it can be int 8, and then it is 1 byte. Okay. So whatever be it in general, so the general choice is so this is the default setting for most CNN library. So in that case, if this is the scenario, then what is my size of network plus operations in bytes? So this is going to be equal to, so what was the total number of such containers? 70,824. 70,824 into 4 bytes. So this is equal to how much? Say approximately equal to
2832296.
70,824 into 4. This is 283,296 bytes, which is approximately equal to 0.28 megabytes. Okay.
So what is OPS here?
Operations. So I mean the size of network. So the is only the all the weights over there, which we had done yesterday. But then we are not considering only weights. We have the weights plus all of these input output which is going over there. So this is my operations over here. Now say that what I have is like this. So in general, when we operate, we do not operate on a per image basis. Okay, we operate in a batch mode. So what happens in a batch mode of operation is that you have some X, which essentially is a collection of lot of these inputs. To XB. Now each of these X small b belongs to the same thing, say 1 cross 32 cross 32. Okay. And capital B is some number. So say B is equal to 64. Okay. Now what you would see is that the size of these operations is essentially size of it will become B times or let me just go like this. Size of X plus size of capital Z1 plus like this up to size of capital Y. Now which is equal to the number of, for each sample there will be a different size which gets generated over there. So that becomes B times size of X plus size of small z1 plus like this up to size of y. Now, if that is the scenario, then this will become 64 into, now you will have to count all of them. So what is that size of X, size of Z1, size of Z, size of Z2, like this. So your learnable parameters are not going to change. Their size which they take is going to remain the same. But for your operations, your operands over there, they will be changing over there. So what will be my size of all of these operations? Sum totaling to? So let us look 1024 plus 4704 plus 1176 plus 1600 plus 400 plus 120 plus 74 plus 10 9118. 9118 and you require 4 bytes to store every single number over there.
Which sum is it, sir? 9118 you count.
9118 is the size of x plus size of z1 plus size of z2 plus size of z3 plus z4 plus z5 plus z6 plus y.
Okay, sir. Thank you.
So we are taking the output of each layer only.
Input plus the output of each layer.
Output plus output of each layer.
Yeah. Because whenever I change the input, my output is going to change. But for a neural network under inference, where you are not updating the weights, my weights are still going to remain the same.
So if we don't mention any batch size, then the entire data set will be passed in the model.
It depends on how you are calling. If you define it as, see, it's not about how it is going to be passed. If your input is a single is a single 3D tensor on a 2D convolution, then the default assumption is that there is only one single sample which goes down. If it's a 4D tensor as an input, then it is a batch of those images. In that case, that first dimension, which is the batch dimension, is what is that value B over here.
Oh, okay, sir. Okay.
So what will this be? 64 into 9118 into 4. That becomes 2334208 bytes.
Hello, sir.
Yeah.
Could you repeat batch mode operation again?
Just a minute. It's approximately equal to 2.33 megabytes. Okay. So what I have in a batch mode operation is something like this. So in general, say this is my network. So my input is X, my output is Y. Okay. Now what is my input going to look like? So my input is essentially a 3D tensor over here, where I have my number of columns, which is N, number of rows, which is M, and number of channels, which is C. Okay. And then comes my output over here, where I had this equal to capital omega, number of classes. Okay, so y belong to r to the power of omega cross 1. Now instead of this, so this is a what we call as serial mode of operation. So I give one input, I get one output, and this is a 2D network. Now, if I have a batch mode of operation, so what I'm doing is I will still have that 2D network. But on the input, I'm going to give you this X, and in the output, I get this Y. Okay. Now, what is this X going to look like? So my X is essentially a collection of a lot of these kind of input 3D tensors.
That's been lot of difference image, right?
Yes, each is a different image over here. And there are B such number of images. As a result of which I get my Y's which is like this, and this also has B such output. So very well, I can say that this capital X belongs to R power of B cross C cross M cross N, and this capital Y belongs to R power of omega cross B. Oh, sorry, this should have been B cross omega.
Sir, B cross omega cross 1 or only B cross omega?
No, this will be B cross 1 cross omega. Oh, sorry, B cross omega cross 1. You are right. B cross omega cross 1. This is what I'm going to get down in case of my Y's. So is this, and this mode of operation is what we call as batch mode of operation. Now, because that is batch mode of operation, so now look over here. My size of my operational space is going to be what is dependent on my batch size, but my size of network is independent of that. So my size of network is what? Size of P1, B1 plus like this up to size of W5, B5, and that is equal to so size of P1, B1 is 156 plus P2, B2 is 2416 plus W3, B3 is 48 120 plus W4, B4 is 10164 plus W5, B5 is 850. This together is 61,706. And this into 4 bytes, which is equal to 246824, which is approximately equal to 0.25 MB. So now if you look over here, what changes in case of batch mode operation is the additional space which you need to account for this whatever your input and output or intermediate activations need to be stored. Okay. So now let me just reorder these two slides. So now if I come from this particular problem, that in a computer system with some amount of memory, with say size of RAM is equal to tell me some size of RAM, 1 GB, 1 gigabytes of RAM. Okay, so what is the batch size for Lec9 5? So can you calculate and tell me this one? What should be the batch size for Lec9 5? So I gave you total 1 GB of RAM, and then the remaining things are over here. Now, based on this one, can you tell me that what will be the batch size for Lec9 which I can operate in computer memory with 1 GB of RAM? And the FP32 representation system. Please try to solve it.
So could you please repeat the question?
So I give you a computer system which has 1 GB of RAM. Now my question is, what can be the maximum batch size such that you can operate this Lec9 in that computer system? So essentially, what is the largest batch size which you can fit within that RAM?
28,120.
How did you come with that?
Sir, I subtracted 0.25 with 1024 and the remaining I divided it by 2.33 and multiplied it with 64. Because
multiplied it by 64. Why 64?
Because we took B to be 64 in the previous calculation, so I used that up.
Okay, okay. So essentially, what comes down is that size of RAM is equal to the size of network plus B times, which is batch size, the precision. So how did I define my precision? I was using some variable, I think small b or something for precision. So capital B times small b times my size of operational space. So this is going to be 0.25 plus B times 4 times 9118, which is equal to 0.25 plus
So can you change the slide?
36. Yeah, so just a minute. 472B. So this is 1024. In term, I'm just writing in terms of MB over here. So accordingly, my B becomes 1024 minus 0.25 divided by 36 472. Oh, wait. This was not written in megabytes. This divided by 10. Oh, I was just dividing it by not 1024, but 10 power of 6. So this into 10 power of 6. So this will approximately be equal to 28069 28,069 images in a batch. So is this clear to all?
Sir, why divided by 10 to the power 6? Sir, please repeat again.
I'm taking it in megabytes. All of these are in megabytes. See that 0.25 was in megabytes. The size of RAM is also in megabytes. So this B into size of OPS. So that should also be in megabytes. So this 36472 is basically the number of bytes it would take. So bytes to megabytes. I just did an approximation over there. I was not dividing it by 1024. I just started dividing by 1000.
Hello, sir.
Yeah.
So just one thing, I just wanted a flow, sir. Like initially when we started, before we went to the batch mode of operation, we first did size of network plus operator. We got 70,824. And we took FP32 precision and 4 bytes each. So it was 0.28 MB, right, sir? Approximately.
Yes. Yes.
After that, we went to batch mode of operation and we took a certain batch size, say of 64. And we carried out the entire operation where the size of ops came to be 2.33 MB and like that, and the nets was 2.25 MB. So like the whole process, why we actually went to batch size when the space was more eventually.
So what I was trying to do is, instead of processing one image at a time, I am trying to see how many maximum images I can fit together so that they can be processed together.
Okay, so we were just trying some like heuristic process, like.
No, not heuristic process. So say I have a bunch of some million images with me and I want to process them. So how can I process them? I read one image. So reading an image means I'm reading it from the hard drive and storing it in the RAM. I process it. Then after that, I go and read another image and do it. Now, instead of that, what I can do is I can load or read a bunch of images together and keep it in the RAM.
Yes, sir.
So the point is, and then I can process all of those images together over there. Now the question which comes down is that what will be that number of images which I can read together and keep it on the RAM?
Okay, given that size that we have just.
Yes. Yeah.
Okay, so this was the flow, right?
So this is exactly the reason why we work on space complexity. I mean, you can do a space complexity analysis, but the question is, what do you gain by that? So the space complexity analysis helps us in coming an answer to this problem over here, that what can be my batch size with which I work.
Sir, like we have given a size of 1 GB RAM, but shouldn't we use some less amount of RAM, like only for this operation we are using a full RAM?
Yes, I mean, what you do is, when I say that you have 1 GB of RAM, it is 1 GB of a segment which is available for your compiler. It does not necessarily mean that you have the whole, like that system has only 1 GB of RAM. So the point of how we come to this one is like, what can be the maximum thing which can be loaded over here? But in general operation, we never load it to the maximum because you will need to keep something free for your system level operations to go on.
Yes, sir. That's why I'm asking, like, if we have if we consider normal system with 16 GB or like that, then how much?
Your memory manager will not allow most of your high level programming languages like Python to have access to all 16 GB.
Yes, sir. That's why I'm asking.
And the partition table will restrict it.
Usually, sir, we see like page of like 24, like 64, 100, and 128 like that. That's why I'm asking, sir. Like this, which number we got? It is like it's a huge number, 28,000.
Number. The reason is your network is very lightweight. You see a batch size of 64 or 32, something of this sort, on much bigger networks, on much bulkier networks itself. So if I have, say, 100 layer network, then you will have 100 layers of those intermediate operation sizes. As a result of which it will require more space, and that's why the batch size will come down. So I'm looking at a CPU system as of now. When you go to a GPU system, the memory is limited, and there this batch size really starts to play a role. So this is sort of consider this to be a toy example. We will give you assignments where you will have to actually solve it for a real practical size network. And in fact, like we will solve it for a
Uh,
VGG16. So when you
so in
solve
the
it for a
GPU
VGG,
type, so in the GPU type, we can process a lot of batches simultaneously. That's where the play comes in, right?
no, wait. Don't go with all of those assumptions. I will exactly show you that what is a batch mode of operation on a GPU and what is that multi-thread parallelism which comes into it. So you can think that you are processing a lot of batches, but essentially you are taking more time because it is interleaving between these batch mode of processing.
Oh, okay.
So let me come to the time complexity, and there is a role play between time complexity and space complexity. So we will have to get
Hello,
into
sir.
that. Yes.
Sir, why is the size of network fixed, sir? Like, won't it vary with the batch size?
How will it vary? Tell me. What is the size
Like
of network dependent on?
in the previous slide, like you have multiplied it with batch size to calculate the size of network.
Where did I multiply it with batch size?
Size of net in the
Size.
last line, sir.
Last line in the size of
Okay,
net.
okay, okay, sir. Sorry, like I was mistaken. Yes, sir.
It is just that 4 is the number of bits per unit memory.
Yes, sir. Yes, sir. Sorry.
Okay, so let's take a short break and then I will start with time complexity analysis. Okay, so the next thing which we look into now is what is called as computational complexity. Now, when you're looking at computational complexity, we need to understand a couple of things. So now let us look into this convolution operation, how it operates. So say this is my input X, and I am looking at one convolution kernel P1 and a bias, which is the scalar element B1. And then this produces my output over here, which is component Y1. So now I can have this one repeating over here like this for the different kernels. Say this is PK and this is you're not able to see it?
No, sir.
Down.
Yeah, but there was a network snag maybe. And this is YK. Okay, so I'm actually writing on a separate tab and that's synced up directly onto this one, and then you're seeing the synced up thing projected on my laptop. That's why there may be a bit of lag. So now if I look over here, then see what will happen. So this each convolution kernel, so I'm looking at the first one. This convolution kernel will essentially superpose over here and operate and then produce this output. Next, it will move to the next location, sort of like superpose again, and then produce my next output. Then it will go to my next location again and produce my next output. And so on and so forth, it keeps on going. Now, for every convolution operation, which I am doing over here, so I need to find out what is my total number of additions and what is my total number of multiplications which will happen. So at a given location, so what is my total number of multiplications for every output location? For every output location. So what is my number of multiplications for every output location? So I have W, H and C number of elements which are multiplied by each other. So there will be C, W, H. Okay. Now each of these elements are multiplied by each other and then you have them added to each other. So that follows that you will have number of additions for every output location is equal to again CWH. So it will be CWH minus 1 number of additions in order to multiply CWH number of in order to add CWH number of elements, plus you will have another addition because of the bias, and this together will make it CWH number of additions. Okay, now are you able to get this thing? How I came to this CWH?
Hello, sir.
Yes.
So should it not be like CWH minus C?
Why will it be minus C?
Sir, because like for each channel we are doing WH multiplications and then we are adding them up. So for each channel it is WH minus 1 and we have C channels.
No. See, what is my convolutions output returns?
Oh, okay, sir. Got
So
it. Got it. Yes, sir.
Y at some alpha comma beta location is equal to what? So this is X at location M, sorry, X at location C comma M comma N times this P at location C comma M comma N, and this is being summed over all M, N and C. This is what my output is supposed to look like plus a bias. So my total number of multiplications is CWH. My total number of additions is also CWH.
Yes, I got it. Yeah.
Okay. So my number of operations, or what we call as number of floating point operations, is equal to 2CWH. Okay. Now, how many number of times? How many times do I do that operation? Number of times of these. This is equal to whatever is the size of my output. That is what I will be doing. So my size of my output is going to be M minus W plus 2PW by SW plus 1 times N minus H. Oh, sorry.
Sir, your voice is breaking down.
Your screen is as well frozen.
Yes, sir.
Hello.
Yes, sir. There is some network issue from your end, I think.
Yes, I was disconnected, but now are you able to see?
Yes, sir. But it's
So now,
lagging.
there might be some lag. Now the point is, number of times of these unit operations is this, and number of kernels is equal to K. So now, what is my number of flops? My number of flops is going to be K times M minus H 2pH plus 2pH divided by SH plus 1 times N minus W plus 2p W by SW plus 1 times CWH. This is what is going to denote my number of, sorry, there will be a 2 which comes down over here. Okay, so you can pretty much like reorder them and write it as.
So why the 2 is coming in front of it?
2 is coming because of here. Did you understand?
Yes, sir, but I have a doubt in the addition part, like CWH minus 1 and plus 1. Like, why are you doing minus 1 and plus 1? I didn't understand.
So, okay. So over here in this part of summation, how many number of addition operations will you have to do? So I have CWH number of elements.
Yes, sir.
So how many times do I need to add in order to get a sum total of CWH number of elements?
Okay, sir, I got it. CWH minus 1 and then again add 1 bias. Yes.
Yes. Okay, so this will define what will be my number of flops for a convolution layer. But then this does not utilize multiply and accumulate, or what is called as this does not utilize fused multiply and add, or FMA hardware acceleration. Now, FMA is a feature within most of the modern processors. Now, what it does is, including GPUs, CPUs, TPUs, everybody uses FMA in order to do it. So in general, what this fused multiply and add would do is that instead of like adding all the numbers, storing it at place, and or like multiplying all the numbers, storing it at place, and then adding it, it would start by essentially doing both multiply and add in the same clock cycle, and that reduces. So what it does in case of an FMA algorithm is something like this. FMA implementation.
So I didn't get what you mean by unit operations. Matlab, those out y1, y2 were the outputs, and why did we? What are we doing with those outputs?
Okay, so in order to calculate the value of this point, how many additions, how many multiplications did you do?
CWH.
Okay, how many additions did you do?
Same CWH.
Okay, so in total, you did CWH number of floating point operations, 2 CWH number of floating point operations.
Right, yes.
Okay. Now again you do it for this location, which will again have 2 CWH operations. Again for this location. So if I keep on repeating like this, I can fill up each of these blanks.
Okay, got it, sir.
So
Yes.
in total, how many such blank spots are there?
OH into OW. So.
Okay. So then it becomes 2CWH into OH into OW.
Yes, sir.
Now I have K number of kernels. So I'm going to repeat that for K number of times.
Okay, sir. Yes, got it. Yes, sir.
So now let's look into what happens in this fuse, multiply and add operation. Okay. So say I have an L.
Sir,
Yes.
I just wanted to ask, what is the flops like in the last slide?
What is the
So, like,
flops?
so FLOPS, like, what is that? Okay.
So this is A0, A1, A2, A3. Like this, it keeps on going up to some A.
So please change the slides.
Okay. And I have another one array over here, which has values like B0, B1, B2, B3, like this, which goes to B of n minus 1. Now, what I want to write down is my output C should be equal to summation over I equal to 0 to n minus 1 of A I B I. This is what I want to implement. Now, this is something similar to what is happening within a convolution as well. Is it so or isn't it so?
Yes, sir.
Okay. So here, what we do is now on top of it, these processors, they will have a two-port multiplier, which is if I give it AI, BI, it produces me a AI, BI. So this is a two-port multiplier. And also I have a two-port adder. So a two-port adder. So what a two-port adder is going to do is if I give it X and Y, it is going to give me X plus Y. Okay, so this is what it is going to do. Now I'm going to make use of these two structures, but do it in a sort of like I always have these two structures available to me, but I can only operate on two elements at a time. Okay, so now what I can do is I go in this way. So initially I have my A0, B0. So what I do is I start like this. I do a multiply of A0, B0. Okay. Then I have my output, which is C0. Say C0. Now what I do is in the next clock cycle, I take this C0 and feed it into an adder. Now this multiplier is free. So here I give A1, B1 and out comes C1. Now, and to this one, I give an input which is 0. Now here that there comes this output C1. What I do is I take this C1 and put it over here. And this output, which is C0, so this is C0 plus 0. This goes over here and then comes another output. And here I have my next multiplier being put. This does A2, B2, and here I have another adder. Wait. What did I do? Alignment problem. So this multiplier will be over here. So this will be B2, this will be A2. So here this one becomes C0 plus C1. Similarly, here this is going to be C2. So this becomes C0 plus C1 plus C2. And like this, it keeps on going. Okay. Now, if you look over here, what I do is this operation is what I run in the first cycle. This is what I run in the second cycle. This is what I run in the third cycle. This is what I would run in the fourth cycle. So now if I have, and then in the last cycle, I don't have any multiplier, I just have an adder, which will come down over there. So now if I have a n array, number of cycles of FMA is equal to what? How many cycles of FMA do I need to operate in order to do a dot product of that n element array?
N minus 1?
No. Look over here. If I have two elements, or as in this case, so I have three elements. So B0, B1, B2. So how many? I did my multiplication of A0, B0 in the first cycle, A1, B1 in the second cycle, A2, B2 in my third cycle. Now I am able to add the output. So output of A0, B0 is available only at the end of my first cycle. So I can take that input to my adder only in the second cycle. I don't have that option of taking this input to my adder in the first cycle. So the A0, B0 thing is something which comes as my input to my adder over here. Now in the second cycle, I have A1, B1, which is equal to this one as C1. That is available at the end of my second cycle so that I can take it as input to my third cycle only. So the output of this adder goes into this one as well as this C1 goes over here. So as a result of which, at the end of third cycle, I have C0 plus C1. Now in the third cycle, I am also able to get down C2, which is equal to A2, B2. And that will require me the fourth cycle so that I can do it. So if my length of array is n equal to 3, I would need n plus 1 equal to 4 number of cycles in order to complete this operation. Do you see that?
Yes, sir. Yes, sir. Understand.
Okay. So now, in case of a convolution, So in case of a convolution, you have this one kind of an operation. CWH of X of CWH P of CWH plus
Sir,
B.
change your side.
So now here you would see that in total here you would need, by strict definition, CWH plus 1 number of ops, because for this bias, and then for this bias what you can do is you can actually add that bias as my initial condition in the second cycle. So in this second cycle, look over here. In this second cycle, I was taking an initial condition over here as 0. Instead of 0, if I take that as my bias, then it will solve my problem. So accordingly, I will require only CWH plus 1 number of cycles to work. Now, if that is the scenario, then my number of flops with FMA is going to change down to much lesser number. Instead of being 2k CWH, now it is going to be k times CWH plus 1 times this m minus h plus 2ph by sh plus 1 times n minus w plus 2pw by sw plus 1. This is what it is going to come out to be. Now look into this reduction. So it has almost been able to halve the compute complexity by using a special structure which is called as fused multiply and add. Now let's come down to the point of doing all of this compute complexity.
Sir.
Yes.
So can you just explain it briefly? Like I missed the maths part. Like how the size got reduced. Sir.
Size did not reduce. The number of flops reduced.
I mean the complexity. Yes, sir. It got half.
Which part are you confused?
Sir, this K into CWH part, sir. Like it got half in that part, sir. I'm confused.
So see, in case of using a FMA to implement this convolution 2D, how much are we writing? I am needing CWH plus 1 number of cycles.
Yes.
Okay. Earlier, if I never had this FMA, then how many cycles was I needing to finish it off? I was needing 2 CWH number of cycles.
Yes.
Okay.
Yes.
So now, if you look into the complete scenario, so the number of flops with an implementation where you do not utilize this FMA acceleration is going to be 2k CWH into this whole thing over here.
Yes, sir.
Whereas when you are using a fuse multiply and add, then it becomes k CWH plus 1. Now, the point is that CWH plus 1 in general will be much lesser than 2 CWH.
Yes, sir. Definitely.
Almost half.
Yes, sir. Definitely.
So that's what I am saying, that we have been able to reduce it to half.
Sir, but aren't the number of operations remaining the same? Only the cycles are getting reduced, right?
Yeah, the cycles are getting reduced. So see, you cannot actually say that the operations are remaining the same. So here multiply and add is a single operation. So that way your number of operations which you need is also reducing.
Okay, sir.
So depends on like whether your unitary arithmetic which you are defining is only say addition, multiplication if they are the unitary arithmetics, or you are defining unitary arithmetic in terms of FMA. Okay, now next is what we call as latency. Now latency is defined as time taken to process an image. Okay, so now let me have only a single 2D conf layer and I define it as 6C 5W 1S0P, and input to this is X, which belongs to R power of 1 across 32 cross 32, and output comes down as Y, which will belong to R power of 6 cross 28 cross 28. Okay, now the point is, how much time do you take to process an image over here? So say my speed is equal to some, what do I say? Give me a variable.
V.
F number of floating point operations per second. That is my speed. Okay. Now, if that is the scenario, then tell me what is my total number of flops for this operation? In this convolution layer, what is my total number of flops? Calculate and tell me. You can assume the FMA. So let me write it. Number of flops underscore FMA is equal to what? K is 6, CWH. So input channel is 1. W is 5, H is also 5. So CWH plus 1 is 25 plus 1 into my output size, which is 6. 6 is already there, into 28 into 28. So what is this equal to? Six into 26 into 28 into 28. So this is 122,304. Okay. So now my time taken to process an image is equal to how much? So what will be my time taken to process an image?
122,304 by F.
122,304 divided by F. So what will that be?
Sir, what is the value of F here?
Okay, so say I have F is equal to, let me take a realistic number. With the CPU, this would be about 10 gigaflops per second. 10 gigaflop per second. So that is 10 gigaflop per second. Then what will it be? So 122,304 divided by 10 into 10 to the power of 9. This is equal to
So 1.22 into 10 to the power minus 5.
So 1.22 into 10 to the power of minus 5 is what?
12.23 microsecond.
Mm-hmm.
12.23 microseconds.
Not 12.23 microseconds. See, it is 1.22 into 10 to the power of minus 5.
Yes. So if we multiply it to 10 to the power 6. If we multiply it with 10 to the power 6, then we will get the value of 12.23. That will be in microsecond unit.
12.23, yes. Right. 12.2 microsecond. So technically, if I am running on a general CPU, you would see that every image, for an image, it is going to take about 12.3 microsecond of time to work. Okay, is that clear?
Yes, sir.
Okay. Next is something which we called as throughput. Now, throughput is essentially defined as number of images processed per unit time. So say my throughput is T. So what is my T going to be equal to? So I know what is my total number of flops in FMA. I know what is my speed. So how can I say what is my total number of images which I can process per second?
So it will be 1 by 12.23 microseconds.
So essentially this is going to be my flop per second divided by my total number of FMA flops. And that is equal to 10 into 10 to the power of 9 divided by what was that value? 122304. 122304. So this is going to give me
81763.
81763. So 81,763 images per second. Now here the assumption is that. So what is the assumption over here? Here the assumption is that all images are processed in parallel. But in case of most modern computer systems, that will not be the case. So you will have a heavy amount of, all images are not processed in parallel, are processed in serial mode. Serial or sequential mode. You will not have parallel mode of processing going on. Now, in most modern processors, that they have parallel mode of processing, and so the throughput actually changes. And in fact, like throughput is not 1 by latency anymore. What will happen is the time taken to process an image is still going to be higher, but the number of images you will process per second is going to be lower by virtue of parallelism. So the point which you were saying that you can actually process more number of images in batches and with modern GPUs. So what you meant to say was that your throughput is higher, but that does not necessarily mean that your latency is lower. Your latency will still be high. So you can actually increase your throughput despite a very high latency by increasing or having parallelization being created in some way. But that's something where we will need to go deeper into all the parallel hardware implementations now. That's something which is not at least part of this syllabus. I'm trying to as much as give you a glimpse about how it happens in most modern systems. But for that, you will have to get through any of these deep learning hardware acceleration kind of courses where you get to know more of it. So last year we had one of those microcredit courses. I'll try to see if we can offer a similar one this year. Then it would be beneficial for you guys as well. Okay, guys, this is where we close for the day.
Sir, I have a doubt. Like, in the last line, you said like the processing time for each image is increased when using parallelism, but the number of images we can process at the same time will increase.
No. So when using parallelism, your latency does not increase. What I'm saying is latency is going to remain constant. Latency is a simple factor on your whatever is your speed with which you can process and how much of operations you are going to do.
Yes,
The only way is that if I have more number of such processing units which are available to be serviced in parallel, then what I can do is I am taking a lot of time, but because I have multiple units which are processing, so the number of images which I can process per unit time is higher.
Okay, okay. Yes, I understand now.
It's a simple pipelining problem. So you have seen those traffic junctions. You would see that your own car is moving very slowly. But if you look into the number of cars which are going through the junction, that is very high.
Yes, sir.
Okay. So let us close for the day now. And then in the next class, I will begin with getting you introduced to practical deep neural networks.
Okay, sir. Thank you.
Thank you,
Okay.
sir.
Thank you then.